Picture this, a fully loaded ship straining against a mooring line in a rising wind. It is hands down one of the most dangerous, highest force situations you will ever witness on board. I mean, if a line parts under that kind of extreme tension, it can be instantly fatal. Welcome back to another explainer. Today, we're exploring the sheer muscle on a ship's weather deck, the extreme engineering that safely controls forces literally measured in tons every single day, keeping these massive vessels secured, stable, and above all, safe. To really wrap our heads around the massive scale we're dealing with right off the bat, just consider this. A large container ship might dedicate up to 3,000 kilowatts of power to its bow thrusters alone. And all of that incredible energy is generated for one incredibly specific reason, just to push the massive ship sideways against the dock when berthing. The amount of mechanical muscle required to just nudge a floating steel city is absolutely staggering.
So here's our game plan for today. 1. Docking and mooring safely. 2. Handling anchors and cargo. 3. Fighting the waves with stabilizers. And 4. Emergency deck machinery.
All right, Section 1, Docking and Mooring Safely. Let's look at the critical machinery that secures the vessel to the shore. You know, what's really fascinating about powering these deck giants is how the technology has evolved. We've largely moved away from those old, fire-safe but super maintenance-heavy steam systems. Today, it's all about highly efficient hydraulic and electrical drives. Engineers love a central hydraulic power pack because it gives you incredibly smooth, stepless control, meaning you get these seamless, high-force changes in speed without the massive weight penalty you'd get from a purely electric setup. Now, when we're actually tying the ship up, we rely on mooring winches, and they use a few very specific components to handle wires under immense tension. You've got the main winch barrel, or drum, which actually holds the line. Then there's the warp end, which we use for temporarily maneuvering the ship with ropes. Add in a heavy-duty gear transmission to transfer power from those motors we just talked about, and absolutely crucially, the band brake. That's a massive mechanical friction grip that holds the drum completely stationary once we're perfectly in position. Which brings us to a brilliant piece of modern engineering, the self-tensioning mooring winch. Think of it exactly like a fishing reel with a really smart drag setting. Tides change, a ship's draft changes as cargo is loaded, and waves constantly cause the ship to surge. Instead of forcing a crew member to manually tweak the lines all day and night, this winch automatically pays out line during a wave surge and then hauls it right back in when the tension eases. It literally keeps the ship snug against the berth on autopilot. But we do have to talk about the extreme danger of these high-tension lines, which raises a really vital question for anyone stepping foot on deck. From a safety officer's point of view, why is the deadly snapback zone marked out based on the geometry of the line, rather than simply telling the crew to stay away from the machine? Well, the crucial point here is that a snapping line doesn't just drop to the deck. It releases terrifying, uncontrolled energy and whips back violently, but it follows a very specific geometry. That mathematically predictable path is determined by the angle of the line and the fair leads it passes through, which might actually be several meters away from the winch itself. So marking the physical, geometric path of that tension is what actually keeps people alive. We absolutely must respect the snapback zone. Okay, with the ship safely secured, let's move on to Section 2, Anchors and Cargo Handling. When it comes to dropping and recovering our anchors, modern ships are so unbelievably massive that they usually rely on a split windlass system. Basically, each anchor gets its own dedicated machine. The heart of this is the cable lifter, often called the gypsy, which has specialized snugs designed to perfectly grip the massive links of the anchor chain. And when you let that anchor go, a heavy-duty band brake manages the release speed. Without that brake, the sheer weight of the chain would just run away with uncontrollable energy. Again, it's exactly like the drag on a fishing reel when a giant fish makes a sudden run for it. Once we're all set at the dock, it's time to move the cargo. In the old days, you'd have these complex derricks requiring whole teams to rig and operate. Today, a single operator sitting up in a high-visibility cab can run a general cargo crane and handle it all. They're controlling 3 distinct movements: hoisting, which is lifting the load vertically; luffing, raising or lowering the angle of the jib arm; and slewing, which is rotating the entire crane 360 degrees to swiftly swing cargo from the hold right to the dock. But hey, before we can even reach that cargo, we have to get the hatch covers open. These are massive steel structures rolling along tracks, and when we're underway, they have to perfectly seal out the devastating power of ocean waves. They do this by being pulled down super tightly onto compressible joining strips using heavy cleats, forming a totally watertight barrier over our payload. Speaking of the ocean's power, Let's jump into Section 3, stabilizers, and how we fight those violent waves. This is honestly one of my favorite engineering contrasts. On one hand, you have active fin stabilizers. These are basically underwater airplane wings extending from the hull that constantly adjust their angle using active hydraulic power to generate lift and fight the ship's roll. Highly effective, sure, but they require the ship to be moving forward at speed, and you've got moving parts exposed to the ocean. On the other hand, you have passive flume tank stabilizers. These are completely internal, they work even at zero speed, and they're activated purely by gravity and the timed sloshing of water between port and starboard tanks. The way a flume tank works is just brilliant, and this quote hits the nail on the head. It works purely on timing, not brute force, like pushing a playground swing at exactly the right point in its arc. By merely timing the natural slosh of water through a restricted channel, a relatively small mass of water acts as a perfect counterweight to brilliantly cancel out the rolling motion of a massive ship. No brute mechanical force, just pure, elegant physics. Now for the final phase of our journey. Section 4, Emergency Deck Machinery. What happens when things go wrong? So let's say a captain needs to maneuver out of a tight spot while moving at speed. They might instinctively reach for those 3,000 kilowatt bow thrusters we talked about earlier to quickly turn the bow. But here's the massive catch. Those thrusters are incredibly effective at low docking speeds, but they lose their steering effect completely as the ship goes faster. Why? Because that powerful sideways jet of water literally just gets washed away by the forward motion of the hull through the ocean. At 20 knots, they are practically useless. And if the absolute worst happens and an evacuation is ordered, we rely on systems like Gravity Davit lifeboats. What makes these so incredible is they are engineered to work safely even in a total electrical blackout. They follow a very strict, purely mechanical sequence. First, you release the gripes and cradle. Second, you trice-in, or pull the boat tight to the ship's side using a wire so the crew can board. Third, you fasten the bowsing lines to hold it steady. And finally, you release it to lower down to the water. Now think about that last step for a second. You are dropping a heavy lifeboat full of people using nothing but gravity. Without a failsafe, that's a terrifying freefall. To fix this, engineers built a centrifugal brake right into the winch. As the boat drops, the spinning motion throws weights outward, creating friction that restricts the descent to a perfectly safe, controlled speed of exactly 36 meters per minute. And it does this with zero electrical power from the ship. Which perfectly wraps up our explainer today and honestly leaves us with a pretty wild dot. If a completely dark, powerless ship can still safely launch its crew into lifeboats using nothing but gravity and friction, what other ingenious failsafes are hiding in plain sight out there on the weather deck? It's incredible how many life-saving systems rely on pure, raw physics rather than a plug in the wall. Thanks for exploring the muscle of the ship with us today, and keep your eyes open for that hidden engineering all around you.